In this section, we're going to be talking about the integral test. So we want to consider the sum as n goes from 1 to infinity of 1 over n squared, which should be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus dot dot dot. Well, how can we determine if this series converges? Well, if we look at the curve 1 over x squared, so the curve here in red, we could also look at the Riemann sum, or if we were to use these points here, we'll notice that this first rectangle has area 1 over 1. The second rectangle, which is 1 over 2 squared, is going to have area 1/4, 1/9, and 1/16, and so forth. So this right here represents that sum. So this is 1 plus 1/4 plus 1/9 plus 1/16 plus on forever. And we know then that that is equal to the sum as n goes from 1 to n of 1 over n squared. Well, based on this observation then, we would be able to observe that 1 plus the integral from 1 to infinity of 1 over x squared dx would then have to be greater than the sum as n goes from 1 to n of 1 over n squared. So the reason for that is this one right here is this, and then the integral from 1 to infinity of 1 over x dx would be all the area underneath this curve. So we're not counting this, we're not counting this. So the integral is an overestimate of that sum. So 1 plus the integral from 1 to infinity of 1 over x squared dx has to be greater than that sum. Well, then we can evaluate this integral. So 1 plus the antiderivative of 1 over x squared is going to be negative 1 over x, and we evaluate that from 1 to infinity. So that's 1 plus, at negative infinity, negative 1 divided by infinity is 0, minus minus makes it plus. We plug in a 1, we get 2. So then, putting this together with this, we have the sum as n goes from 1 to infinity of 1 over n squared is less than 2. So then that tells us the sequence of partial sums is bounded above by 2 and bounded below by 0. Also, this sum, since we're only adding positive things, is always getting larger. So the sequence of partial sums is always increasing. So, combining these two facts, we have that the sequence of partial sums is a monotonically increasing bounded sequence. And from our theorem from chapter 11, section 1, we know that a monotonic sequence that is bounded always converges. So, therefore, the series converges. So the integral test combines those things that if we can bound an increasing sequence, a monotonically increasing sequence of partial sums, we'll make a connection to functions. So the function is going to have to be decreasing, and we'll see that in a second. Then we will know that the series converges. So in our handout section from Blackboard, if we go into our lecture notes, we have a summary of a whole bunch of stuff from series and sequence. So we just went over the integral test. So this list in here has everything, but it's going to have the hypotheses for our integral test and when we can use it. So to summarize, the integral test, if an is greater than 0 for all n, let an equal f to the n, and if the integral from 1 to infinity of fn dn converges, then the sum converges. Also, if the integral from 1 to infinity of fn dn diverges, then the sum diverges. So they share the same fate. All right, let's go ahead and do a couple of examples. So we wish to test this series for convergence or divergence. So first thing we note is we have to check, is an always greater than or equal to 0? And the answer is yes. Our an is 1 over n squared plus 1. N squared is always positive. A positive plus a positive is positive. And a positive divided by a positive is positive. So our an is always greater than 0. So then it says we need to evaluate the integral. And I'm going to write it in terms of x's instead of n's because it doesn't change the value of the integral. So 1 over x squared plus 1 dx. And we recognize that as being the arctangent, so that's the inverse tangent of x evaluated from 1 to infinity. The inverse tangent of x at infinity is pi over 2 minus the inverse tangent of 1 is pi over 4. So we get the value of that integral is pi over 4. So then, by the integral test, the series converges. All right, let's take a look at our next example. So we want to do the same thing. So our an this time is 2n all over n squared plus 1. And for n greater than or equal to 1, we're going to have that the numerator, a positive times a positive is positive. And n squared plus 1, so a positive plus a positive is a positive. So we once again have a positive divided by a positive, which is positive. So an is always greater than 0. So the integral test applies, and now we need to integrate from 1 to infinity of 2x all over x squared plus 1 dx. So to evaluate this integral, we'll use the u substitution, u equals x squared plus 1. Then du is equal to 2x dx. Substituting into our integral, we're going to have, if x is 1, 1 squared is 1, 1 plus 1 is 2, so the integral from 2 to infinity, squared is infinity, infinity plus 1 is still infinity. And in the numerator, the 2x dx becomes du over x squared plus 1 is u. So the antiderivative of 1 over u is the natural logarithm of the absolute value of u. And we evaluate that from 2 to infinity, which the natural logarithm of infinity is infinity, so the integral diverges. So the series also diverges. Alright, let's take a look at our next example. And then after that, it's going to be a u try. So what we need to test is an bigger than 0. We have an equals sine n. And if we check a sub 3 is equal to sine 3, and the sine of 3 is less than 0, so an is not always greater than or equal to 0. So we can't use the integral test. And it turns out we don't even need to, because if we take the limit as n goes to infinity of an, or in this case, the limit as n goes to infinity of sine n, this limit does not exist. So in specific, if it doesn't exist, it's not 0. So the series diverges by the test for divergence. Alright, so now it's time for your u try. Alright, so the an's in this case are always positive, so let's just jump right to our integral from 1 to infinity of 3x squared all over x cubed plus 27 dx. So once again, it's going to be a u substitution. So u equals x cubed plus 27, and du is equal to 3x squared dx. So we change our limits of integration. So we plug in 1. 1 cubed is 1 plus 27 is 28. Infinity cubed is still infinity, and infinity plus 27 is still infinity. So then our 3x squared dx becomes a du divided by u. So once again, we get the absolute value of the natural logarithm of u evaluated from 28 to infinity, which is infinity, and that diverges. So since the integral diverges, the series also diverges. Alright, so the next thing we want to talk about is a specialized form of the integral test. And this can often be used instead of the integral test for certain simple series, and it can be combined with some other tests. So it turns out that it is pretty helpful for doing certain things. So the p-series test is the answer to the question, well, for what values of p does the series, the sum as n goes from 1 to infinity, of 1 over n to the p converge? So by the integral test then, it's the integral from 1 to infinity of 1 over x to the p dx. So to do that integral, we rewrite it with a negative exponent, so x to the negative p dx. Then by the power rule, we add 1 to our exponent and divide by it. So we get x to the negative p plus 1 divided by negative p plus 1. And then we evaluate that from 1 to infinity. Well, we need to know for what values this is going to converge. And the term in the numerator, the x to the negative p plus 1, will only converge if the x is in the denominator. So to move the x into the denominator, the exponent has to be negative. So for the integral to converge, negative p plus 1 must be negative. So if we have negative p plus 1 has to be less than 0, and we add p, and that's going to give us that p has to be greater than 1. So the series will converge when p is greater than 1. So if we look at our sheet here for our summary, we have our p-series, and it says that we know for our p-series that the sum, as n goes from 1 to infinity of 1 over n to the p, converges if p is bigger than 1, and it diverges if p is less than or equal to 1. So let's go ahead and look at our next set of examples. So determine if the series converges or diverges. So we have the sum as n goes from 1 to infinity of 1 over n cubed, and this is going to be a p-series. P equals 3, so it converges. Here we have to do a little bit of rewriting. So the square root of n is the same as n to the 1/2. So that's also a p-series, but p equals 1/2, so that is going to diverge. All right, and the last one is for you guys as a u-try. So once again, we rewrite by putting our exponent into the denominator, and now it's a p-series. And our p equals 1/3, so this one also diverges. All right. It's worth noting that the integral test only tells us about the convergence and divergence of a series, not the value of its sum. So, for example, we have the sum as n goes from 1 to infinity of pi squared over 6, but if the integral test is used, so let's go ahead and apply that. Oh, I see. We're missing part of our sum and there. So this should have read the sum as n goes from 1 to infinity of 1 over n squared. So if we apply the integral test to this, we would have 1 over x squared dx is equal to the integral of x to the negative 2 dx, which is negative x to the negative 1, evaluated from 1 to infinity, which is negative 1 over x, evaluated from 1 to infinity. So negative 1 divided by infinity gives us 0, minus makes it plus, 1 over 1 is 1, gives us 1. So the integral test converges to 1, but that is not the sum of the series at all. And if we go back to the beginning, that should make sense, because remember, the integral test is an estimate, and we're calculating the integral, so we're not adding up any of this space. The actual sum of the series is the rectangles. So there's always going to be error when we take the integral. But evaluating the integral, as we've seen, is often much, much easier than actually trying to sum up a series, which is, unfortunately, pretty difficult. So that leads us to the following: estimating or approximating the sum of a series. So, estimating the sum of a series, any partial sum is an estimate of the value of the series, but how good is the estimate? So the remainder of a series, we're going to define that to be r sub n, and the remainder of a series is the actual sum s minus s sub n. So a1 plus a2 plus a3 plus dot 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 on forever, minus all the way out to an. So that's going to reduce out all of the terms. The only thing that's going to be left for our remainder, r sub n, is a sub n plus 1 plus a sub n plus 2 on forever. And our hope is that that remainder is going to be pretty darn small. So if we were to draw a picture of the remainder, so we're all the way out here, we have n plus 1, n plus 2, same thing, n plus 1, and n plus 2, and we have some function. So when we look at our remainder, we could think of it in two possible ways. So one possible way is if we start at n and we use the right endpoint, so say right here, we would get an approximating rectangle that looks like this, and then our next approximating rectangle would look like this. Well, we could do something similar, but instead of using the right endpoint, we could use the left endpoint. And if I did that, that would give me something that looks like this and something that looks like this. And when we look at each of these, we notice the rectangles that are in green would be an underestimate, as we've seen, and the rectangles in blue would then be an overestimate of the sum. So combining these facts, we would have that our remainder, r sub n, which is equal to a sub n plus 1 plus a sub n plus 2 plus dot dot dot, would have to be less than the integral from n to infinity of f of x dx. But our remainder, r sub n, which would be equal to the same thing, a sub n plus 1 plus a sub n plus 2 plus dot dot dot, would have to be greater than or equal to the integral from n plus 1 to infinity of f of x dx. Combining these facts together, we then have that the integral from 1 to infinity, or from n plus 1 to infinity, of f of x dx is less than or equal to the remainder of the series, which is less than or equal to the integral from n to infinity of f of x dx. So the remainder is trapped in between these two things. So that means that our error is then trapped between these two things as well. Or we can use it to help approximate. So let's go ahead and do an example using this approximation. So example 4. Approximate the sum as n goes from 1 to infinity of 1 over n squared by using 20 terms, and then find a bound on the error. And then, second part, how many terms are required to have an error less than 0.0001? Okay, well, let's grab our graphing device, and let's see what a 20-term approximation looks like. So we grab sigma, and we have the sum as n goes from 1 to 20 of 1 over n squared. Now our calculator thinks for a second, and we get 1.5961, and we can compare that to the known value, which is pi squared over 6, and we get 1.644. So that's our exact value, and that's our 20-term approximation. Well, let's check our error bound. So from what we have here, we need to calculate the integral from 21, because it's from n plus 1, so we're going to have the integral from 21 to infinity of 1 over x squared dx is less than or equal to the remainder, which is less than or equal to the integral from 20 to infinity of 1 over x squared dx. So our antiderivative of 1 over x squared is still negative 1 over x, and we evaluate that from 21 to infinity. And our antiderivative is still negative 1 over x, and this time we're going from 20 to infinity. So at infinity we get 0, and then minus a minus, so we get 0 minus minus is a plus. 1 over 21 is less than or equal to our remainder, is less than or equal to 0 minus 1 over 20. So then this tells us the remainder of our series is somewhere in between 1 over 21 is less than Rn is less than 1 over 20. So if we were to approximate those values, so 1 divided by 21 is 0.047, and 1 over 20 is going to be 0.5 or 0.05. Excuse me. And so we know that the error in our series, or the remainder of our series, is somewhere between 0.047 is less than Rn is less than 0.05. Okay, so that means that our remainder of our series is somewhere in between those two numbers. Well, let's check that. So if we go pi squared over 6, and we subtract from that our series, so n equals 1 to 20 of 1 over n squared. We press enter, and we get this value. And we'll notice that indeed the actual amount, which we were able to find this time, so our remainder, which is this value, is in between those two things, right? So the actual remainder that was left was 0.04877. So we were only able to do that because I happened to know that the sum of this series, as n goes from 1 to infinity of 1 over n squared equals pi squared over 6. In general, we won't know that and be able to verify it. So this gives us an indirect method for determining the remainder of the series. And that leads into our second question, which is, how many terms are required to have an error less than 0.0001? So that means we want the error, or the difference between these things, to be less than 0.001. Okay, so how are we going to do that? Well, we know that the remainder, based on what we just had above, that our remainder, Rn, is less than or equal to the integral from n to infinity of 1 over x squared dx, but it's greater than or equal to the integral from n plus 1 to infinity of 1 over x squared dx. So we want the remainder of our series to be smaller than that value. So if that's the case, we want this to be less than 0.001, which then, by chaining these together, this is what we want, is this to be less than 0.0001. Because we don't know how to calculate Rn directly, but we do know that Rn is less than this. So then what we want is this piece. So we evaluate our antiderivative again, which is still negative 1 over x, but this time we're evaluating it from n to infinity, which is going to equal negative 1 over infinity is still 0, minus a minus is a plus, 1 over n, and we need this to be less than 0.0001. So we need to solve this equation for n. So we have 1 over n is less than or equal to tenths, hundredths, thousandths, 10 thousandths. So I'm just going to write it as 1 over 10,000. So then, if we multiply both sides of our equation by 10,000 n, here the n's cancel, here the 10,000s cancel, and we get n is greater than or equal to 10,000. So to guarantee that much accuracy, we would need to add up 10,000 terms in that series. All right. Now it's your turn. So how many terms are needed for the error in the sum as n goes from 1 to infinity of 1 over n cubed to be less than 0.0001. We're pretty much going to have the same thing, but our integral is going to be a little bit different, so it's going to be the integral from n to infinity of 1 over x cubed dx, and we need this to be less than or equal to 0.0001, so tenths, hundredths, thousandths, 10,000ths again. So the antiderivative of x cubed is going to be negative 2 over is going to be, so we have x to the negative 3, so that's going to be x to the negative 2 divided by negative 2, which is going to be negative 1 over 2x squared, evaluated from 1 to infinity. So at infinity, we're still going to get 0. Minus minus makes it a plus. When we put in 1, we get a half. Or sorry, not a half. We have n squared. I wrote that down wrong. N squared, so we get 2 over, or 1 divided by 2n squared. And we need this to be less than or equal to 1 over 10,000. So we multiply by our LCD again, which is going to be 10,000 n squared. So we have 10,000 n squared, 10,000 n squared. 1 over 2n squared is less than or equal to 1 over 10,000. And once again, all of our fractions should reduce out. The n squareds go. 2 goes into 10,000 5,000 times. 10,000 and 10,000 reduce out. So we get n squared is greater than or equal to 5,000. Taking the square root, we get n is greater than the square root of 5,000. So we calculate the square root of 5,000, and we get 70.07, so n has to be bigger than 71, because you can't add up a 0.7 of a term. So to have the desired accuracy for that series, we would need to add up 71